Okay, so welcome back, and now we're going to do some examples of dealing with rational functions. Okay, so now I'm going to show you with limits, but what we're really doing is I'm going to show you the technique, but once you understand the behavior and you recall the behavior of rational functions based on the relationship between the degree of the top and the degree of the bottom, you'll see where these go automatically. Okay, and all I'm using is the fact that polynomials are differentiable everywhere. So if I take the limit, so that they want us to take the limit of this thing as it goes from to positive infinity and negative infinity. Yeah. So now I'm going to take the limit. Well, let's do it this way. So I'm going to take the limit as x approaches plus or minus infinity. Okay, and you'll see why I put the plus or minus there in a moment. Okay, I'm going to do the limit of this whole thing. So 3x minus 1 over, 2x. 2x plus 5. Now before I do this, notice that this function, right, in college algebra or pre-calculus, we would ask ourselves, okay, what's the end behavior of this thing? Well, we would notice that the degrees are the same, or we would divide the top and the bottom by the largest power of the bottom, and then again ask ourselves what's happening as x gets really, really big negative or really, really big positive, and that would tell us what the behavior would look like. So we know, based on our experiences from algebra, that this is going to go to the line 3/2. Okay, there's a horizontal asymptote at y equals 3/2, and so as x gets really big negative or really big positive, that's where it's going to head. But let's prove it using limits. Okay, it's one thing to see and understand where it goes, but it's another thing to show that, hey, that indeed is where it goes. So let's do the limit. So limit as x approaches plus or minus infinity. Again, because the differentiable, continuous, we can split it up using the quotient rule, right? So this will be the limit. Oh, actually, before we do that, let's multiply the top and the bottom by the largest power of x. So if I do that, so I'll get f of x is equal to what? If I divide the top and bottom by x, I get 3 minus 1 over x divided by 2 plus 5 over x. Now you can see as x gets really big positive, these two terms go to 0. Or if they go to negative infinity, if x goes to negative infinity, they're still going to go to 0. So either way, it's going to 3/2. Okay, so now, let's change this to, well, how do I want to do this? Yes. So let's do that. And this is one of the techniques you're going to see, because again, if you notice, if I was to do the limit of the top and the bottom the way it is now, I'm just going to get infinity over infinity, which is an indeterminate form. So that doesn't tell us anything. But watch when I replace it with an equivalent form of it. 3 minus 1 over x, 2 plus, 5 over x. Okay. Now, this is equal to the limit as x approaches plus or minus infinity of 3 minus 1 over x over the limit as x approaches plus or minus infinity of 2 plus 5 over x. And then of course, now because of this polynomial, again, differentiable, I can just do term by term, right? So this constant just becomes a constant. So this is going to be equal to 3 minus the limit as x approaches plus or minus infinity of 1 over x divided by 2 plus the limit as x approaches plus or minus infinity of 5 over x. And in both of these cases, what's the limit of those two fractions? 0. So I get 3 minus 0 over 2 plus 0, which equals 3/2, which is exactly what I said it was going to be. Okay, now let's do the next one. So the next one, notice that the degree of the top is less than the degree of the bottom. So if the degree of the top is less than the degree of the bottom, then this thing's going to have a horizontal asymptote at y equals 0. But let's use limits to prove it. Okay? So again, I'm going to divide the top and the bottom by the largest power of x, which is x cubed. So if I divide the top by x cubed, I get 3 over x plus 2 over x cubed. And this is going to give me 4 minus 5 over x squared plus 7 over x cubed, right? Now, same thing. Because I'm dealing with polynomials on the top and the bottom, I can differentiate them using the quotient rule, right? So now I can say the limit as x approaches plus or minus infinity, and again I'm using plus or minus this time, now I'm going to use 3 over x plus 2 over x squared divided by 4 minus 5x squared plus 7x cubed. Okay, right? And so now that's going to be equal to the limit as x approaches plus or minus infinity of the top, which is 3x plus 2 over x squared, divided by the limit as x approaches plus or minus infinity of the bottom, which is 4 minus 5 over x squared plus 7x cubed. And again, I can do this term by term, right? So this is going to equal the limit of this one, right? So it's going to be, I'm not going to write it out, but you can see that the limit of this is going to go to 0. The limit of this is going to go to 0. This is going to be 4. This is going to be 0. This is going to be 0. So what I'm going to get is, I'm going to get 0 plus 0 over 4 minus 0 plus 0, which is going to be 0 over 4, which gives me 0. So the limit is 0, just like I said. Okay? Now, notice on the third one, the degree of the top is more than the degree of the bottom. Okay? But also notice that it's exactly 1 more than the bottom. So again, I'm going to write f of x, and I'm going to divide the top and the bottom by the largest power of the bottom, which is x. So in this case, I'm going to get 3x plus 4 divided by 1 plus 2 over x, right? Now, what happens is this thing is I take the limit, okay? So if I take the limit, now this is, I'm going to split it up, okay? because of this right here. Here, it doesn't matter if x is negative or positive. As x gets bigger, this thing is going to 0. Not the case here. If x is negative, going to negative infinity, this whole thing is going to be negative. If x goes to positive infinity, then this whole thing is going to be positive. So it does matter. Okay? And as x goes to positive or negative infinity here, this is going to 0, so this is going to end up being positive on the bottom. So this x value here controls the sign of the whole thing, as you can see. So here I'm going to do x approaches positive infinity first. Okay? So I'm going to get 3x plus 4 over 1 plus 2 over x. And of course, I can do the limit of the top and the bottom. Okay, so now, what am I going to get? Well, the top is going to positive infinity. The bottom is going to 1. So it's going to positive infinity. Now, if I go to negative infinity, well, guess what? Now, this is going to negative infinity and this is going to 1. So it depends, right? So if you're going to positive infinity, this thing's going to positive infinity. If x is going to negative infinity, it's going to negative infinity. Okay, and that's it. Now notice, one more thing I want to show. If you do long division, right, so remember I said earlier that there's an oblique asymptote. You should remember this from college algebra. If you take the, what was it? It was 3x squared plus 4x over x plus 2, right? Yep. Okay, so now, if I divide by x plus 2, right? Let's do long division. So x plus 2, 3x squared plus 4x. Okay, so we get x here, and so we get, 3x. So 3x will give us a 3x squared, and then 2 times that will give us a plus 6x, and then we subtract, right? And then we get 0 plus negative 2x, right? And now, what happens? Now I'm going to do it again, right? So now, what do I need here? I need a minus 2. So x times a minus 2 gives me a minus 2x. And then here I get plus 2 times negative 2 gives me a minus 4. And so now if I subtract, well, now I get 0 plus 4, and now that's my remainder. Okay? Now, the thing about this is that this quotient here, that is the equation of the line. Notice it's a straight line. That's the equation of the line that represents the oblique asymptote. Okay? Because when you divide this, what you end up getting is you end up getting 3x minus 2 plus the remainder divided by this. So it would be 4 over the divisor, which is x plus 2. So this is your quotient, which represents your oblique asymptote. Okay? Okay. That's it. I think that's all I want to say. Okay, have a great day.